Okay, Assalamualaikum everyone. Jadi, we'll start the first tutorial, the first question of the second tutorial actually. So the tutorial this week is on DC motor. So we will have, um, I think total of 7 questions, which we will discuss in this tutorial. I know it's quite a lot. I try to constrain as much as I can, but this is like the basics of all the different types of DC motor that we need to analyze, and for us to be able to come up with the top speed characteristics of the motor, we have to understand the construction as well as the calculations or analysis of each of the motor. Okay, so the first question is regarding a shunt DC motor. So shunt is a parallel connection between armature resistance and field resistance, in which they share the same terminal voltage. Okay, so in this question, you have a compensating windings. Okay, so with compensating windings, you will have a constant flux running inside the machine regardless of the load that you put inside the machine. So when we talk about load, it means like we are connecting some sort of applications to the shaft, to the output shaft of the motor. So if we increase the load or decrease the load, the flux will be constant inside the machine, and that helps to maintain the output characteristics of the motor, and therefore it is desirable lah. Okay, that's why we have a compensating winding. Now, it has an armature resistance of 0.06 ohm, and the field circuit has total resistance. So here, R total is already calculated. Okay, so remember that R total is basically R adjusted plus RF, and this is already calculated here as 50 ohms. Okay, and this produces a no load speed of 1200 RPM. So there is a no load speed. No load speed means there isn't anything connected to the shaft of the motor, which is ideally, we assume that IA is equals to 0. Okay, so armature current inside equals to 0 when there is there is no load attached to the shaft. Okay, so no load current refers to no load armature current refers to that IA equals to 0. Okay, so now it also says that the shunt field winding has 1200 turns per pole. So there is an F there. So in this case, since we don't have armature reaction because of the compensating winding, we don't really have to calculate anything regarding this field winding. Okay. Okay, so the first question is find the motor speed when the input current is 100 ampere. Okay, now when there is an input current, okay, of 100 ampere, so that means somehow there is some kind of torque that was put to the shaft of the machine, or the other way, that there is some load at the shaft of the machine. Okay, so remember that the no load speed is 1200 RPM. So now there is some load because the input current now, instead of 0, it becomes 100 ampere. So so right now we want to know what is the motor speed. Okay, alright, so in our knowledge right now, the only speed that we know is the speed at no load. Okay, speed at no load, which is 1200 RPM. Okay, so at no load, we can have few variables that we know, which is armature current equals to 0. So when the armature current equals to 0, we know directly from the circuit here that because EA is connected like this, right? Okay, R total and then LF. Okay, since this is DC here, so this is just simply straight away connected like this. And if it is 0 here, IA equals to 0 here, so the voltage, there is no voltage drop around here, no voltage drop, right? There is no IARA. Okay, this is equal to 0 because IA is 0. So obviously this branch only have EA, and this EA is equal to whatever voltage drop that we have here. It is either we can calculate by IF times R total, or from the VT itself, because this here is VT. Okay, so at this point, when the no load speed is 1200 rpm, we know that IA is 0, and also EA at no load is equals to VT. Okay, so this is the information that we know from the question itself. Okay, now let's see the relationship between the speed and the internal generated voltage. We know that EA is actually K prime V and M. Okay, this comes from the theoretical knowledge that we know before, that internal generated voltage is equals to the machine constant K, okay, and become prime because we have speed in RPM here, and then the flux in the system, as well as the speed of the machine. Okay, now because we have compensating windings here, right, we know that the flux is constant. Okay, so regardless of the load, so the flux will be constant. So EA at no load, for example, and N at no load here, right, the K is the same machine, right? So if we have EA at some kind of speed that we want, okay, the K is the same, obviously, sorry, the K prime is the same, and the phi is constant, so it's the same, and N at this speed, okay, will be, well, now we will have this equation, and from this equation we know that this can be cancelled because it stays the same, right? EA no load over N no load will be equals to EA speed, some speed, and then N some speed. Okay, so from here we will see that because of this constant flux and the machine constant K remains the same throughout the operation, whether we have change as the speed changes, we know that we can actually find the speed of this motor if we know first of all EA at no load, speed at no load, and then the EA at this speed. Okay, alright, so let's see. The first question says that if the line current is 100 ampere, now we know that from the equation, from the circuit, we have IE and IF, and then this is the line current, right? Okay, so input current 100 ampere means it refers to the input current here, okay, IL. Now the input current is 100 ampere. Okay, now how much is actually IE? IE is IL minus IF, okay, because at this node IL goes in, it branches out into IE and IF. Okay, so to get IE is IL minus IF. So here it's 100 ampere minus IF is actually VT over RF, or R total. Okay, so VT is 250 volts divided by 50 ohms, and then we get here 95 ampere. Now, we know that at 100 ampere input, the current or the armature current is actually 95 ampere. So EA, okay, when IL is 100 ampere, it's no longer simply VT over RF, because now we have a voltage drop here. Okay, now we will have a voltage drop here. So EA is actually VT, not simply VT, but it is minus IA RA. Okay, so it's 250 minus 95 times RA, which is 0.06 ohm. Okay, and this will give you 244.3 volts. Okay, now we already know the EA at this speed, and we want to now know simply what is the speed. So EA at no load over N at no load is equals to EA at this speed that we want to know, and then we actually can find the speed that we want to know. Okay, so EA at no load, we know it's 250 volts, speed is 1200 RPM. Now this EA that we just found out, which is 244.3 volts, and this is actually the speed that we can know, that we want to know. Okay, so this speed is equals to 1173 RPM. Okay, so basically we know that the no load speed is 1200 RPM. Now with the increase of the load, okay, because there is a line current of 100 ampere, obviously we know that there is load attached to the shaft, the speed now reduced to 1173.